That's so weird. Okay. Seems to be working. If I'll probably stop sharing my video and then just do a screen share. Okay, and then I'll share my entire screen because we're going to be looking at this visual aid that I prepared here, which I just adapted this straight out of the book that I've been recommending to everyone, which is Get Programming with Haskell. So at the beginning of Unit 5 in the book, it's called Working with Type in a Context, which I think that title alone for that unit can be helpful for us to kind of zoom out and remind ourselves what the common theme is of all of these abstractions that we're looking at. It's all about being able to work with data that has a higher amount of structure and complexity to it, and that poses some challenges, right? Because what we're always trying to look for in functional programming, so like our end goal all the time is code reuse and composition or composability, right? That might be a better term to call this. We want to be able to define very generic operations that we can reuse in many cases, and then we want to be able to compose those small operations into like long pipelines or chains that we just kind of feed data in one side, and it gets progressively transformed along the way. And ideally, we want to be able to do that in a single line of code, right? We don't need to have our whole program defined in a single line, but each like atomic piece is going to be its own little like micro function or operation. And then when we construct our entire program logic out of those pieces, we want to be able to do that in a nice, elegant, like single line chain if possible. And data that's in a context, when we're working with types in a context, they pose some obstacles to doing that, right? Because it's not so simple to take more structured and complicated data and just feed it into a pipeline like that the way we can with raw data. So take, for instance, like if we've got like some list of integers and then like we want to transform those integers, or maybe we have a list of strings and we want to do some transformation that's going to like, I don't know, maybe map like the length of the strings, and then like we want to maybe now we're dealing with a list of integers, right? We've transformed it, and then we want to maybe do some other operation on those integers. We can, map another mathematical function onto the results of the first thing. And as long as we keep finding functions that match the correct type signatures of the different transformations that we want to do, then that's very straightforward. We just compose those functions together, and no matter how many different transformations are taking place at each step, we have a pretty simple type of data that's just getting passed along to the next stage. But once we add some kind of greater complexity there, maybe we're now operating in a context where a value might not exist. Like we're doing some mathematical operation and we're doing division, for instance, and there's a possibility that we could be dividing by 0 at some point, and we want to have a safe version of that division function so that we're not having our nice, elegant pipeline blow up at runtime when we're actually calling it. We want that possibility of absence of a value to be somehow factored into the way that we design our program. And if that null or non-existent value pops up, we want that to just propagate through the entire pipeline and not have the pipeline break, right? So in order to do that, we basically need adapters that we can use to act as the sort of connector points between the different pieces of our application. And that's what functors, applicatives, and monads are in the simplest sense. So we don't need to find any kind of like bizarre convoluted metaphor for what they are. Like, we can think of them as adapters, and the reason we need those adapters is to facilitate composability and reuse, and that's all they are. And you know, we have a kind of hierarchy or progression of these three different types of adapters. We need to have something be a functor first before we can turn it into an adapter that has more power than that, like an applicative, for instance. So like at each step as we move up that hierarchy, we're just adding power and flexibility to our adapter and giving it the possibility to compose and be used in different types of situations. So I took these diagrams from the intro to Unit 5 in Get Programming with Haskell, which starts on page 327. And I think that these diagrams are really helpful to get a visual look at things rather than just looking at type signatures and writing code. You know, this kind of helps use a different learning modality to kind of cement in what the purpose of this is and what each of these things are doing. And these are based on different scenarios that we might run into where we're trying to work with different types of data and we're running into obstacles with being able to compose it together, right? So if we just have simple data like this that doesn't have any kind of structure, you know, that this is expressed in a really generic way. So you can basically substitute any type in here for type A, any simple type, and any type for type B. So this could be a function from, like, say, an integer to a bool would be a good example. And then if we want to write a simple function to be able to make that transformation, then the type signature of that function is just going to be int to bool. And to apply that transformation, we know how to do this already, right? We just call the function f and then put its argument after it like this. And when we run f on A, we get B as our result, some data of type B. But then once we add some kind of context, so now this is also, you know, very generic. We could think of this little pink wrapper around this as maybe being a maybe type or an IO type, any kind of additional context or structure that we're adding wrapped around our data, right? And it's not so easy to compose when we've got data in this format, because we now can't call f on MA, right? F takes a type A as its argument. So if we give it MA as the type of input data, it's going to give us a type error and not compile. So if we want to take a piece of data from type MA, and here M is just it's a type constructor, right? So this is substituting for any one of those possible contexts that we might have, whether it's maybe or IO or list or function. Like, it's open-ended here. I'm using the letter M because that's what's typically used to express a monad, and I want to use that same nomenclature for all three of these. But you know, a functor doesn't have to be an applicative or a monad, right? It could just be a simple functor. So in that case, in the type signature, you might see f of A, but I'm using f up here as a function, and I don't want to conflate that f in two different use cases there. So M is just our kind of arbitrary variable here that we're considering to be representing the context that the data to the right of it is inside of. Hopefully that makes sense. So we want a function from MA to MB, right? And we can write that ourselves. I called this DIY function, right? Because we have to basically build this from scratch. And we've seen how to do that before, where we might just do some kind of simple pattern matching. So if I have, we'll call my function G here, and I want its signature to be maybe A and return maybe B. And I guess to make this super concrete, let's actually fill in some concrete types here. So G is just going to be like a simple predicate function here. And we're going to use destructuring and pattern matching to write this. So we have two possible scenarios of what our input argument could be, right? We have, it could be nothing, in which case we want to return nothing, right? Or it could be just of some x. And in this case, we want to maybe check whether that value is greater than 0 as a real simple example here. So I want to call greater than 0 on x, but we need to make our return value match the type signature that we're looking for here, right? So what do I have to do to complete this?
If statement.
Put it just before.
Yeah, put it just before it. We just need to wrap it in just, right? So this is an example of a simple DIY function that solves this kind of problem. If my original function was just, if my function f had the signature into bool like this, and I wanted to basically say that f of x equals x greater than 0 like this. I've now been able to translate this so that it now works in a possible scenario where my my x value is non-existent, right? But this is now a highly specialized function that only serves that one particular use case, right? And if I want to maybe have another function h or something that would check like whether the value is even, then I'm going to have to keep rebuilding this and using this as like boilerplate code every single time and doing this explicit destructuring, pulling the value out of it, and then doing something with it. And in the case of IO context, if we're dealing with IO ints here, I actually can't do this type of pattern matching and destructuring, right? Because what did Irfan say, that the IO is like the Hotel California? You can check in, but you can't leave, right? So we can't actually like pull that value out. So there's some cases where even like trying to do this clunky little DIY solution to something won't even work because we're not able to do this type of explicit pattern matching. So what we want is some way to be able to basically apply f itself without having to invent a G to do this, and then be able to apply f in multiple scenarios, and also outside of the use case of just checking some predicate on a number. Like we also want to be able to have that same functionality with any kind of function that that could be taking in a maybe value as its input. So that's where I wrote here, this approach isn't dry, right? Because we're supposed to follow the maxim in programming, don't repeat yourself. And we don't want to have to be inventing G, H, I, J, all these different functions for all our different use cases. So the first adapter is a functor, which allows us to preserve our original simple function that we defined up here, f, and take some kind of structured data like a just integer and apply f onto it and get either a nothing or a just int back as our result. So functor gives us the first step towards having like full composability with this contextualized data type that we're dealing with, in this case, maybe. And so I wrote out two different ways that you can use fmap. You can either use this prefix notation and write fmap like this, and then the first argument you pass to it is your function, which has type A to B. And then your second argument is some value of type MA. And what fmap basically does is kind of hoists or lifts that simple function into the context that you're dealing with. So the context of maybiness, essentially, and allows it to just be applied in the same way that we were just applying f of a up here in the simple function. So we now don't need to rewrite g. And that's already given us a lot of utility, right? So if I wanted to do the same thing that I'm doing here, all I would have to do is like I could define g prime as taking some value that's like we'll call it mx, right, for maybe x, and it's literally just going to be f mapped onto mx like that. No multiple patterns required, no destructuring, pattern matching, anything like that, right? We just lift this bad boy up into the context, and then it does its thing like we would expect it to do when it's in its simple form. Does anybody have any questions about that? Is this explanation helpful, or is this too basic and too much review? Because I wanted to start from the very beginning and kind of build up, because all of these things build off of each other. Okay. Everyone good? Okay. Yeah, and so what we're going to do after I go through all of this is we're going to actually build our own maybe from scratch. We're going to assume that the maybe type hasn't been added to Haskell yet, and we want to add this functionality in. And we have the classes of functor, applicative, and monad available to us already. So what we need to do is design a custom data type that functions in the way that maybe would behave, and then we're going to instantiate it in each of those classes, and then we'll be able to get the full functionality that maybe already has using these little adapter operations, right? So the next step up the hierarchy are applicative functors, and these are often just called applicatives for short, but the full term is an applicative functor, and I think it's important to remember that, because then we recognize that an applicative isn't really a completely distinct thing from a functor. It's kind of a functor plus plus, right? It's a functor that has like some additional power of what it can do. And we'll see that when we look at the $, this fmap operation here, we'll see the syntax is almost identical to this. And that shows you how this is basically just a functor, but now we're in an additional situation where our function itself that we're trying to lift into the context is already in the context itself. And we want to basically apply that contextualized function to a contextualized value. So we see how it's behaving the same way as a functor. We've got a function on the left and we've got some structured value on the right, or contextualized value. And we use this infix operator to kind of lift it over and allow it to do its thing. But applicative is allowing you to actually apply a function that is more complex, as if it were in its raw or naked form. So that's what it allows. So that's one scenario here that an applicative solves. It also solves this scenario up here where, say, we have some kind of function, and I'm calling this MAB. This is a kind of naming convention that you can use for functions sometimes to make it a little bit more clear, because we see what the actual inputs and outputs are in the name of the function. So an MAB means something that's going to take an MA and return a B. And that naming convention can be a little weird at first because we're used to just using letters like F and G and H and stuff for functions. But if you can wrap your head around the fact that this 3-letter abbreviation is a function, it's not a regular piece of data, right? Then it becomes very easy to see whether you're using it correctly, because notice how I have a function called MAB, and then I'm calling that on an MA. So we know that if we like sort of subtract the MA part out of the function here, then we're going to get a B as our resulting value. So that makes it really clear. If this is called MAB and I'm trying to call it on something that's just A, we know that that's not going to work, right? Because there's a type mismatch there. So a lot of times when you're kind of instantiating your own functors, applicatives, and monads, it's helpful to use this type of naming convention in the variable names so that you can kind of stay on track mentally for whether you're doing the correct thing. So pure helps us in this situation where I've got some function that is expecting a contextualized value. It wants an MA, right? But it returns a value that's just of type B. And I actually want an MB as my result. I want, say, a maybe B. So pure gives us the ability to just take any non-contextualized data and just lift that value up into the context that we're working with. So if I take MAB and I feed it an MA, it's going to give me a B. And then all I need to do to get it to be an MB is just call pure around it on the entire result, right? And that takes my B to an MB. So that's one component of an applicative. And the second component is this application operator here, the TIE fighter, right? So this solves 2 problems. There's basically 4 problems that we can deal with, like that we're going to encounter, right? One is that we've got some piece of structured data. We've got a function that wants unstructured data and returns unstructured data. And we want to be able to pass structured data into that and get structured data out. So like that's what mapping means, right? We transform the inner values while preserving the outer structure around it. So that's one like kind of composition roadblock that we might hit, is a scenario like this. Then there's 2 more where we might have a situation like this. It's a bit more of an odd situation, but like in this case, the problem we're having is that our output data doesn't have the structure that we wanted it to have. So in this case, we use pure to solve that. the third case is when our function itself has some kind of additional structure around it, and we want to be able to apply that to structured data and get structured data out. So that's where app comes in. And then the last case is when we've got a function like this with signature AMB. This function takes in a simple unstructured piece of data of type A, but it returns structured data of type B. And we want to be able to pass structured data or contextualized data into that function and basically like force this structured thing into something that's expecting something unstructured. So I always call this the like the plunger operator, because like you're trying to get something into like a pipe, right? And it's too big and it doesn't fit. So you need to have something that kind of creates pressure to like force it into that narrow entry point. And that's what this bind operator does for us. And this is extremely useful because like we have say we have a sequence of operations that we want to do in a pipeline like manner, and we don't want to define all of those functions so that they take structured data in. If we do that, then we're basically back into this scenario here where we're having to like add additional pattern matching and case analysis into every single one of our functions that we make, when it would be much easier to have this function just take in an integer, right? And then it can return a maybe, potentially. In this case, the function's so simple that we wouldn't really see the utility of that. But like say that this function is actually a divide by zero function or a safe div function. And this is going to, what we'd like this to take in is a simple integer, and we'd like it to pass out. Actually, it's going to take two integers, right? We'd like to have this return a maybe int like this. But if we're going to do this operation multiple times and chain them together, then and probably we would do some kind of partial application in that case, right? So we would have like we'd be calling it on some like initial value, and then like we would want to keep like dividing that by the result that comes from that. So we don't want to have to make this so that it is accepting maybe integers in order to repeat it and create a pipeline with it, right? We want this function to have the simplest type possible inputs so that rather than doing this manual unwrapping of the values, we can just work with X in its pure form, right? So that's where bind comes in, is it allows us to define our function. We're still going to have our function maybe is returning some kind of just int, right? But at least we don't have to deal with the scenario of whether it's nothing or not and unwrap the X and work with it. We can just treat that as if it's a simple integer. And what this operation does is if this MA value that's coming in is nothing, it will just automatically return nothing as the result. The value propagates down the line, and we don't have to worry about that kind of manual case matching. So that's the fourth scenario that we'll run into where we have difficulty composing things, and the monad adapter gives that final piece to be able to do that. Okay, so how's everybody following?
Can you share that mirror?
Yeah, I'll share this at the end of class. I probably won't be able to keep this here forever because I have a limited number of free boards that I can use, and I'm using all 3 of my free ones right now at this point. But
Yeah, just even a screen capture of it would be fine.
Yeah, you can screenshot it and maybe even export it or something once I share the link, and I'll keep it up for a while because I don't need it for the time being. Maybe I'll make it a little prettier too. Cool. So it's not so long and it could fit in like a single image to export. So are we ready to try and build our own maybe, or do you guys want me to go over any of this a bit further before we start?
Oh, we can jump in.
Okay. All right, cool. I'll keep this up here so that we can look at it. Maybe zoom in so we just have functor, applicative, and monad here. So what we need to do to start is we're going to need to define a data type. We're going to call it my maybe, and it has to have one type variable, right? Because we need to refer to what the type of the data that's contained in the just case, or what will be our equivalent to just. So I'm going to make a simple sum type like the way that maybe is defined. Instead of nothing, I'm just going to call it no. And instead of just, I'm going to call it yes, but a just value also has whatever that type of data is that's contained inside of it. So it's either no or yes of A. And I'll just derive a couple things here. I don't know if we'll need them or not. We'll probably need show at least. So now we can start using this exactly the way that we use maybe, but in order to get these kind of code reuse and composition benefits, we're going to have to make instances of the 3 different adapter type classes, right? So we'll start with functor. We do instance, functor, maybe, where. And the linter is going to give us a clue already of what we need to do next, which is saying we need an implementation for fmap. So we need to define how fmap will work. And fmap is kind of similar to that DIY version that we made. But the difference here is we're only defining it once for our maybe type, and then it will now work regardless of what the value, what the type rather of A is here. So we don't have to re-implement this function over and over again. So fmap is going to take some function f, and actually I can, we'll use the type signatures in the instance declaration here. Fmap has type, takes a function from A to B. It takes a value of type maybe A, returns a value of type maybe B. Right? If you're not using GHC 9.0 and up, you have to add a language pragma at the top to allow this. It's called, I think it's called instance SIGs. So if you're using GHC 8 and you don't do this, if you try to put a type signature in your instance declaration here, it will give you an error because you used to not be allowed to do that. So you'd have to turn it on with this. But I'm using GHC 9, so I don't need to do that. All right, and then we have two possible patterns.
Shouldn't it be my maybe in the type declaration?
Oh, correct. Yeah, thank you for catching that. Perfect. Okay. So how can I implement fmap here? We've got two possible data constructors for our maybe type, right? So we need to make a function pattern for each one of those cases. It's the next parameter that needs to go here.
Okay.
We've got f here is corresponding to this, right? That's our first parameter. And then our second one is going to be our my maybe value, but there's two possibilities that can be. So we need to write a pattern for each of those so that we have exhausted the possible inputs that this could take. So the first one is going to be no, right? And in this case, what would I return?
Nothing.
No.
No, yeah. And maybe it's nothing, right? Here it's no, because we can't reuse that name. And I don't want to call it nothing prime because it'll confuse things, I think. So, and we can replace this f with the wildcard pattern, right? Because we're not using the function when we have no value to map over it. Now we need to define the second case, which in this case, we're going to just destructure this into yes, x, and then what comes next?
fx. You apply the function to the x itself.
fx, yeah. And what's missing here that's giving me this error?
My maybe fx.
My maybe is the type constructor, right? This is a value, so we need a data constructor for it. But that's correct. That's the type that we're looking for is my maybe. But we need to just provide our data constructor here and make it a yes, right? Are you guys comfortable with this $sign operator now? If I use this, is it clear what this is doing, or would it be clear if I use parentheses? Because I don't mind either way.
Well, that's good.
It's okay now.
Okay. All right. So now we've got a functor, and we can actually test this out. If I do something like, let's do fmap multiply by 2 on a value that's yes. And we see that it's working now. The fmap is lifting this function into the yes context. It's like kind of lifting it over this yes wrapper and applying it onto the value that's contained inside, right? And if we want to see the flexibility of this, like let me try to think of a string operation we could use. Here's something interesting. If we import data.char here, just so we can do some more interesting string stuff here. Now let's say I have I've got a maybe string, so we'll call that yes Haskell, and I want to make all of the letters uppercase, right? I can do fmap, and then I'm going to have to map to upper. Oops. Come on. All right, let's do it. Let's actually just make a little function here that does that. So not even a function. We're just going to name it something so we can load it, and I don't have to type it in there. So I've got yes, Haskell, some kind of maybe string, right? Or a my maybe string in this case. And I want to basically map the to upper function onto it. But I've got to get over this extra layer of structure, right? Because we have 2 layers of structure now. We've got the list context, because this is a list of characters, right? So that's one like level of structure that we have to surmount or overcome. And then we've got an additional layer wrapping around it, which is a context of potential absence, a context of maybiness, right? So I can do fmap and map to upper onto this my maybe string, and then it will do what I'm expecting. So if I just check foo, and now we've got the value that we expected, right? So you see the flexibility here of how it doesn't matter what type of data I'm dealing with. Here we've got something even with an extra layer of complexity to it, to something like a simple list, and I was able to do that as well. But if I were to try to do the same thing, but instead of a yes string, I've just got a no, right? Then it's going to give me no. And I didn't have to build in that propagation of nothingness. It's already handled in the generic sense by the way that I defined fmap. So I don't have to re-implement these patterns for every single type that I'm doing. And that's all a functor is. It's an adapter that allows us to transform data inside of a context while preserving the context in the end result. Is that clear?
Yes.
All right, so we'll move on to doing an applicative instance now. One thing that's a little tricky is knowing when you need to put this type variable in here. Notice how our type is actually my maybe a, right? But when I'm defining these instances, I don't include the a here. And that has to do with the kind of when you look at these. Same with Monad as well, too. These are all types that have a kind where they're expecting some type to come in, and then they return a concrete type, right? So if I defined this as like functor my maybe a, then I would be providing just a star here instead of a star 2 star here. So that's a little bit tricky to understand. But in the case of like the either type, if I was to do my either looks like this. Where we've got let's see, maybe we can use Spanish for these so we don't have to reuse left and right, right? So we do izquierda y, or is it derecha or derecha, Brian?
Derecha.
My Spanish is derecha. Yeah.
Yep. Oh, and Mike was hot. That's cool.
That's fine. So here we've got two type variables here because we're taking their functionality like a little bit higher than a maybe, right? In the case of maybe, when we've got a bad case, we just return a simple null value that doesn't contain any type of data. But like in a more complex type like either, we actually want to contain some data in the bad case as well too, and that data can have a distinct type from the type of data that's contained in the happy case here. So we could also call these sad and happy. I like to do that sometimes when I'm building my own either. And you guys might be wondering, like, what's the point of doing this, right? Because all of these types already exist. But the reason that we do this is because it's the best way to practice understanding all of these different abstractions, and then that sets us up to be able to create our own types that don't exist already. And we're going to be seeing in Plutus, there's a lot of different custom types that are specific to Plutus, and they'll have these type of instances defined on them, and we need to understand how those work as well too. So generally, like all the chapters in the Haskell programming from First Principles book, the chapters on functor, applicative, and monad just have you like implementing your own versions of these already existing types, just to familiarize yourself with the process and the steps that you go through. So this either type actually has, notice the kind of this is star to star to star. And what we're looking for to define a functor instance, an applicative instance, or a monad instance is just star to star, not star to star to star, right? So if we're going to do a functor instance for my either, we need to put the first one of those type variables here. We need to apply one type to it. And I didn't specify what class I was doing. So now this matches that kind signature that we're looking for here. We've sort of partially applied one of our types to either, and that's given us the kind signature that we want, which is star to star. In the case of maybe, maybe only has one type parameter here. So in order to satisfy the kind signature that the functor instance is looking for, we just put my maybe and we don't apply that. Is that making any sense at all? I mean, this stuff is really abstract and difficult to explain, and this is the first time that I've ever explained this, so I'm not sure if this is coming through or not, but I just know that when I've gone through these exercises many times, defining all of these different things, this is one of the things that trips me up, is like whether to include the type variable and how many of the type variables are included. If we had like some third case that was like, what can we call this? Say we had a third kind of constructor here that was like really sad X. Now see how this just broke, because now the kind signature for my either is star to star to star to star. And functor needs star to star. And the kind signature of this now, since I've only applied one of these variables, is star to star to star. So I would have to do this, how it works. So kinds are a little bit tricky to understand, and you know, it's just something that you have to kind of look at many times and get a grasp on what the syntax of these actual instances is. But let's return this to the case where it's like the real either. And I'm going to implement a functor instance for this as well too, but I'll just do it quickly. You can see the difference. By either E, A. E is the type of whatever the error message is going to be, or error result. A is what we'll get in the happy case, right? So far everything is the same as my maybe. It just has this extra type parameter in it, right? And in the case of sad, this is just going to return sad E. And in the case of happy X, we're going to return happy F of X. Oh, what did I do wrong here?
I should happy A.
Yeah, but I can use any. I can use any variable
yeah.
name for this. Yeah, so that's not the issue, but couldn't match type B with A. Expected my either EA actual. Oh, I wrote the signature wrong, right? Because we're mapping. So when we have the happy case, we actually want to transform the data. So it's going to become some new type B. But take a look at the two of these. I'll share this file after, and just understand the difference. That like the reason that we had to include one of our type parameters here is because my either has 2 and maybe has 1. So like however many of those variables you have, you're going to subtract 1 from them when you actually define these instances. So my either goes from 2 to from my either EA just to my either E, and my maybe A goes to just my maybe. Because we can only to like have a functor obey the kind of mathematical laws that it's supposed to have, which we haven't gone into too much, but like it basically has to do with like identity and associativity. Those are two things that need to be preserved when we have a functor. Like if the functor has 2 different possible options like this, each containing their own data, only one of them can actually have the transformation applied to it. The other one needs to be left alone the way it is. So when we map over an either, we don't transform the data that's contained in the sad case. We just return that exactly the way it is, and we leave it alone, right? And then we only transform it if it's in the happy case. And that's how a functor needs to behave. If we had this have F applied to it as well too, now we violated the laws of how a functor is supposed to behave. And we've also created a situation where now E and A actually have to be the same type. And that's not what we want, right? We want to be able to return, say, a string as an error message in the sad case. And we want to return, say, an integer or, whatever other type of value in the A case, but in the happy case rather. But we want to have the flexibility to be able to have those not share the same types. And if they don't share the same types, then we can't apply the same function to them. So this makes no sense to actually have the mapping take place in the error case. The same way it doesn't make sense to apply a function to a null value, right? Because there's no value to actually apply it to. So we treat this sad case, even though it is containing some kind of data that we're going to pass along to the user, that's still essentially behaving the same way that a null value does. All right, so hopefully that's clear. That was a bit of a tangent, but let's define the applicative instance for my maybe, and then maybe it could be an exercise to try it and do it for my either as well too afterwards. So I'll leave that as a little challenge, I guess. We have two different things that we need to define, right? We have pure, and pure has the type maybe A. And pure is basically just equal to yes, right? What's it saying here? Oh, this is not correct. It's A to A. Pure is a function, right, that takes some non-structured data and then wraps it in the structure. Pure is equal to yes. I wrote this in point-free style by omitting the parameter, but this is the same as this, right? Takes an x in, gives a yes x out. And that has just solved this case over here in our diagram, where if we run into some scenario where we want something in a structure and it's coming out in a raw form without being structured, then we can just use pure to lift it up and get it into the structure, right? So that's pure. And now we need to define our apply operator here. And this takes a function of maybe A to B, and it takes a value of type my maybe A, and returns a value maybe B. And so we're going to call that function MF, just like I did in my diagram here, so that we remember that it's a maybe function, right? And then it's got some, actually, let's call it MAB. And then got some, no, there's a reason that I didn't call it MAB in that case. It's because this bit makes it seem like it's a function that, like in the first case up here, right, where actually not just the input value to the function is wrapped in the context, but the entire function itself is. So that's why I called that MF. And then it's going to have some value of MA. And we're going to have to add additional patterns here, but this is the basic situation, right? So the two possible cases are we could have a no function at all, right? absent function. And then whatever this value is over here doesn't matter because we have no function to apply to it, right? So in that scenario, we're just going to return no. We're going to propagate the error down the line. In this case, we can think of the reverse scenario as well, too, where now we have a my maybe function, but we have no value to apply it to. The value is missing, right? So I use the wildcard again for this case because it doesn't matter what the details of the function are if we have nothing to apply it to. So we just ignore that, and we also return no in that case. Any questions about what I just did here? Everybody's really quiet, so I want to make sure that I'm not lost.
No, doing good.
Okay, cool. So now we need to define the non-empty pattern, right? So this would be, we've got a function that's in some maybe context. Then we've got some maybe a value. And we can actually implement this in terms of fmap. Let's try deconstructing it just to make it a little more clear. So this is a yes function in this case, right? Because otherwise we would have matched this pattern here. So we know we have a function and it's wrapped in a context of yes. And now what I could do is the type signature of f, if it'll show that to me here. I think I might need to put something here, but f is my simple a to b function like we had in the most basic case up here, right? And we've already solved the functor adapter that allows us to take that simple f function and apply it to a structured value, which we call MA, right? So what can I write here to give me the result that I'm looking for?
What are you trying to do?
Yes, yes F de A. Yes F de A. F A.
So what I'm getting at here is that if I can access just the raw function that's inside of this my maybe context, right? That's what I did here with the pattern matching, is because I wanted to just get f. So now I have an f which has a type signature of a to b, right? And I'll put a little comment here so that we can see this real clearly. F has type a to b, right? And this here, my MA has type my maybe a, right? What can I do to get the end result I want, which is my maybe b? We can use something that we've already defined and make this very simple. Because look at the functor adapter over here in the diagram. You see the different types that we have here. Here's our simple f function from a to b. And now we've got a piece of structured data that it has type m of a, right? Which is exactly what we have here. and this is my end result that I'm looking for, my MB. So what is the syntax that I need to put here to be able to achieve that result?
Oh, so call probably so yes, and then $, and then apply the function to your input, right?
So we don't need yes at all here, because using the functor adapter is going to give that to us already. But the rest of what you said was correct. So try to rethink it about what the syntax is that I need to write here.
Oh, okay. So would it just be so your yes and then your TIE fighter operator and then F and input, right?
No.
So
It's
you
like otherwise
use
it's gonna
fmap.
Yeah, we're
Sorry.
gonna use fmap. So we
And-
have two different options of how we can do that, right? I put the two of them here. So you can take your pick whether we want to use prefix notation and actually write the function name out, or whether we want to use the operator. I think probably we should use the prefix notation with fmap, just so that this is a little more clear, because we might not remember what this $1 means yet. We
Yeah,
haven't
I
used
agree.
it too much. So. Okay, so what do I have to write here to actually flesh this out?
So just fmap and then fma.
Exactly. You got it, Brian. And we can see why we don't need to actually rebuild our yes constructor here, because the type signature for fmap takes a function of type a to b. That's our f variable, right? And then it takes a value of type f of a. Here we're using f as our kind of wrapper type constructor, right? I used m in my diagram so that it doesn't get confused with the f. But this f here isn't the f in our function. This is operating in the type level, so it's a completely separate thing, right? That's where some of the confusion can come in. But this f is my maybe, right? That's the actual type that's wrapping it and giving it the structure. So we have a function from a to b. We have a value of type my maybe a, and the end result after we call it is going to be my maybe b, which is exactly what the return type of our TIE fighter operator is, right? So that's why we don't need to actually put yes around it. It already is a yes. And if we put a yes around it, then let's see what happens. Now the type that I've got here is my maybe B. See? fmap already gives us the structure that we're looking for. That's why we designed that adapter, because it does the lifting into the context for us by default. And if I put this redundant yes here, then my type signature now no longer matches, because I've now nested two levels of maybiness that I don't need. Does that make sense? I can see why it would seem like we needed to put that there, because we've been doing something similar in the way that we defined fmap for both my maybe and my either. We were actually kind of rebuilding our context. But the thing is that since we've already done that, and an applicative is already a functor, that means we don't have to do that again. We don't have to do any manual like wrapping, because fmap is doing that for us already. So hopefully that's becoming clear, how we're sort of like building each layer of utility on to the one that we had before it. Now the last one, maybe we can test this real quickly. Let's see how this works. So if I have a first we want to be able to put something into a context, right? So if I have a string like this, and I want to make it a my maybe string, see that our pure operation is working, right? Because when I call pure on banana, it turns it into a yes banana. So that piece works. And now the next thing we want to do is, let's say that we have a yes function, which is going to be I don't know, just multiply by 2 again, I guess. So we've got this multiply by 2 function, but it's embedded in this kind of structure, right? Because somewhere in our application, there's a possibility that this function could not exist. And instead of having a yes times 2 here, I could have a no, right? So that's the scenario. It's a little bit hard to make that concrete of where we would run into a situation like that. And that's why Irfan was going through those very detailed examples of like different scenarios to show you guys where you would run into the need for these things. We're going to take a kind of contrived example here and not really consider why we would have a function inside of a yes context or a maybe context. We're just going to go with it, right? And then I've got a some number here. Oops, not a string, a number. We'll see that it's working, right? It's taking this function, unwrapping it out of its yes context, and then f mapping it over the context of the integer that's contained in there. So it's like an unlifting and then a lifting back into the context. That's how applicatives work. So you guys can take a stab at trying to do an applicative instance for my either. And then the next step after that is to think about other monads that you might want to deal with and re-implement them. There's some other examples if you have the Haskell from First Principles book. I think that this Get Programming with Haskell book is a lot better at explaining in a more down-to-earth and pragmatic way what these things are and why they're useful. But to like really get into the nitty-gritty of like how the different monads that are built into Haskell behave and how you would re-implement them if you were doing them yourself, then the Haskell book is better, the First Principles book, because it really pushes you to like implement every single common monad that you would deal with, from the functor step all the way up to the monad step. And getting that muscle memory and practice is what's necessary to make these things become less of these kind of weird abstractions that are like living in a vacuum somewhere in your brain and connecting it to the actual underlying mechanics of how it works. Because like there's none of these functions are super complicated, right? This apply function, fmap, and even bind that we're going to do are not super complicated. It's just that they're so distanced from like the kind of day-to-day concerns as programmers of where we would use them until we make that connection and link the two together. And that just takes time, and it takes exposure to it in different forms and in different ways. And gradually it just clicks and starts to make sense, and you won't be pondering what a monad is anymore. You'll just be using monads and not thinking about it. last one, my monad, or sorry, not my monad instance for my maybe.
Excuse me, Jan.
Mhm.
We don't need to make the other side MA apply to yes F.
Can you repeat that? Sorry, my volume was a little low.
On your line 31,
Mhm.
we don't need to make the other side, the associativity, MA multiply apply to yes F.
So the signature of this always has a function on the left side of it,
Oh,
and
okay.
the
Yes,
value
yes.
on the right, which is it's a little
Yes,
it's a
understood.
little weird. Yeah, it seems kind of like flipped almost, sometimes. But yeah, that's just how it works. I think that there might be some equivalent that does it in the reversed way, because usually with these type of operators in Haskell, there's a different version of them. And for instance, with bind, this is the standard way of writing bind, right? But this exists as well, which is like a left oriented, or I guess, yeah, it's going from right to left instead. So like you can bind in the opposite direction like that, which would be the like monad equivalent of what you were just asking with this apply operation. I'm not sure if there is an apply operation that is flipped like that, but there's a chance that there is, because usually Haskell provides the flexibility to do things in different ways like that, depending on what your preference is. Because some people are coming from a language context where they're used to like using pipe operators to like compose functions together. So those are like a left to right kind of composition, whereas like true composition following the way we compose functions in math goes from right to left. So there's different like directionality to a lot of these built-in functions that gives you the flexibility to do it in the style that you prefer. But the kind of idiomatic way to do it is that you have the function on the left side and it's getting sort of lifted, is the term that's typically used, into the context and then used in that way. And same with bind, like you're not going to see this right to left bind as much. I kind of wish it were the other way around, because like bind is actually sort of more like a pipe operator than like compose. And to me, that kind of trips me up sometimes, because when you're doing composition using bind, it's often making you think in the reverse direction than you're used to thinking when you're just using like the dot operator to compose different functions together, right? This would be like, function 1, and then you compose that to function 2, and then you compose that to function 3, like that, and you just keep chaining them together with the dot. But like your initial value is going to be coming in from the right side here, pass to this function, then pass to this function, and pass to this function like this. But with bind, your initial value is actually coming in on the left side and going into your function. So those are some of the kind of nuances that you have to just like get familiar with and be able to think sometimes left to right, sometimes right to left. I don't know why they decided to do it that way, but
Okay, thanks.
okay, so we've got two things that we need to define here in our instance. You used to need to define return here because monad was actually introduced before applicative, and then applicative was introduced later. So this is a comment that I made in class last time, that return and pure are basically the same thing. and return was providing that functionality that pure does in the applicative class, but it was part of the monad class. And then when they added applicatives, they renamed this pure and they moved it into the applicative class because, like, in terms of mathematics, that functionality of what pure does is part of the definition of an applicative, not a monad. And a monad is an applicative by definition, right? It's an extra layer of functionality beyond that. So monad has this pure ability already. But in the old school style of Haskell, before applicatives were introduced, you would have return X defined in the same way that we defined pure up there. And this would go in the monad instance. Now, I believe you can just omit this entirely, but you'll often see when people do monad instances that they just define return being just a synonym for pure, because we've already implemented pure and we don't need to do it again, right? But now you can use return or pure interchangeably. The preference that most people recommend is to use pure rather than return, because the idea is that return is poorly named and it creates a confusion with imperative functions, where you have a return value being something that essentially terminates your function and outputs a value. And that's not what this return function does in Haskell. So, like, it can cause confusion for beginners who are not properly making that distinction, and that's why you'll see a lot of people recommend just like never using return at all, because pure does the same thing. I don't think pure is super well named either, because you know, in functional languages we talk about pure functions and functional purity and stuff like that, and this use of pure doesn't have anything to do with that. And you could be like taking a value and lifting it into the IO context by calling pure on it. And then what you're really dealing with in the end is an impure value, right? And you're using a function called pure to create it. So that's another, I think, like unfortunate naming choice in Haskell that you just have to sort of learn and understand and work around. Then the second one is bind, right? Let's look back at our diagram to remember what bind is doing. We've got some function with a signature A to MB, right? So we're calling that AMB. And then we've got some contextualized data MA here. And we want to have our plunger operation that will allow this to fit into this function so that we can just get an MB as a result. So we have two possibilities with our myMaybe for what this MA can be. It can be a no value, right? And then it doesn't matter what our AMB function is here. This is just going to return no. Because if we've got nothing to push into the pipe, then nothing comes out. Hopefully that makes sense. And then over here, we've got possibility. The second pattern here is going to be yes. That's X, right? Put this in parentheses to make it a little more clear. Parentheses are not necessary though. So we've got this structured value, and then we've got some function A and B, and maybe I'll name this A too, just to make it more clear. Then it should be pretty straightforward to figure out what I need to put here, right? If we look at the names of those variables, the way that I named the function and the way that I've deconstructed my structured value here. what would I need to apply here to make this give me the, oh, I didn't write the signature here. Big omission because we want to see that. We don't need to write the signature for pure, right? Or for return rather, because it's the same as pure. So bind has type, takes a value of type my maybe A. It takes a function from A to my maybe B, and it returns a value of my maybe. If I put a hole here, it'll show us what it's looking for. We've got our type signature here. We're looking for a my maybe B as our result. And it will show us the signatures of the different pieces that we have to work with, right? We've got AMB, which is of type A. When we give that an A, it gives us my maybe B. That's the return result that we're looking for, right? And then we've got a value A that has type A. So what do I need to do here?
A and B, A.
There you go. Very nice. Now again, this might seem a little bit counterintuitive at first, right? Because we're expecting that like this is going to, that we're going to have some kind of yes value here on the right side to give it the structure. But the reason we named this function A and B is to make it real clear that we give it an A and we get an MB out. And MB is what our return type of the function is. So all we have to do is feed this in an A. The A and B function is giving us the yes that we're looking for already. So we don't need to manually add it. The same way as with the applicative, if I were to like wrap this in this, now we're going to have a type error and we're going to have that extra layer of nesting, right? It's going to say expected a my maybe B, and now we've given it a my maybe B, which we don't want. So that's another common mistake to make, is like thinking that you need to like do your own wrapping here. The function itself, our function A and B, actually produces a wrapped value on its own. And now we can think of a scenario where we could use this. So if I've got, I want a little function that takes takes an integer and it produces a my maybe integer. And all it's going to do is it's going to take, if that integer is equal to 0, then it's going to produce the no value, right? And otherwise, what we're going to do is just take like 1 if yes. Let's put this here. I already called something foo, so you know what we got to do now. We got to make it bar. And this needs to be wrapped in And we can actually use our pure now to create this. I could have just put yes here, right? But I wanted to actually use pure to show you what this is doing. Because this is reusable. We don't need to remember what the like default wrapping is for our type. If we know that it's an applicative, then all we have to do is provide pure and it will wrap it with the correct value. So that's my little test function. And what we're going to do is we're going to take a value, which is going to be yes, yes 0, and we're going to bind that into bar. And we get a no. You see what I was able to achieve by creating that that monad instance? Because like this is a my maybe integer. It's not an int, right? Which is what bar is looking for. But now I've got a plunger that I can take that value and push it in. And if I were to do this multiple times like that, notice how the no value is propagating through the pipeline. It actually sort of breaks at this point, right? Because we're trying to divide by 0. So this becomes a no. And then I'm able to just keep feeding that no into bar as many times as I want. Let's try it with a value that isn't. Try it with 1 instead. This is a really stupid function. I'm sorry. It's just hard to think of like, you know, more real world examples when we're trying to just get at the fundamentals of what this does. But you see what's happening here? So what's basically like using the plunger to push the raw integer into this this bar function, and then it's checking the pattern. If it's not 0, then it's dividing 1 by that value. We could maybe make it a little more interesting if we made it like 100. If I reload here and then we do like, say like yes 10 and put that into bar, then we get yes 10 out. But then if we add another one, it's still just apparently this just returns, the way that this works, it just returns the same value every time. But you know, you see the difference between what happens when I give it a no or when I give it a yes, how it's able to just continue. And I could, you know, imagine that rather than just repeatedly calling the same bar function, I had some other functions that had similar signature to this, right? I can just now compose those all together and my data is maintaining its structure as it goes through that pipeline. And I wasn't able to do that before. I would have had to like completely bootstrap the entire thing by myself for every possible like combination of inputs and outputs. And we now have that composability because we've created a monad. Any questions? Cool. Probably gonna gonna wrap up then, if this is clear, but I'll share this code with you. I'm gonna take out the kind of like testing stuff that I did, and maybe you guys could also find more useful examples of how you could actually apply this on your own, which would probably be a better learning exercise. But the sequence operator. So you're talking about this one, right? So let's take a look at the type signature of that. So sequence is one of these operations that you get for free when you've defined something as a monad. So to make it a monad, we just need to define how bind works. And then we get all of these other monadic functions are now usable for us on our custom type that we created. And one of these is sequence. So you don't need to manually define how sequence works. You manually define bind, and then you get sequence for free. So what this does is it basically takes a value that's in some kind of monadic context. So think of this as like a maybe A, or an IOA is probably better, right? And then like an IOB, and then it just gives you an IOB at the end. So it basically just works like the bind operator, but it doesn't pass a value on after it's done. So when we made that chain with our bar function and we're using bind, each time it's taking the result of the bar function and passing that on to the next function in the chain. And what sequence does is it discards the value that's returned from the function to the left side of it, and it basically just will like execute whatever that thing does, but not pass the value on. So that's why sequence is frequently used with something like put stir line like this, and then we might have some other like function coming after this. Like put string line just prints something to the console, right? And its type is IO unit, meaning like a void, or I shouldn't call it void, but a non-existent value. It's just like a blank thing, because all this function does is it's executing an IO action. It's performing some side effect, right? But the value that gets printed to the console does not get returned. Notice this is an IO unit, not IO string, right? So if we have a sequence of different IO functions that we want to execute to like call different side effects. So like we maybe want to run another one after that and do that. These are going to be on different lines, so we'll just do it like that. And then maybe after printing that, then I wanted to get line, and then say I wanted to take the string that the person gave, and I want to bind it into map to upper. Will this work if I give this a name? Something's wrong with my type signature here. So Yeah, I'm all right. So what this last part isn't important. Let's just look at it like this, because when I'm trying to like create a long like IO composition here, normally you would use the do notation to do this and do it sequentially, and then it would be more clear what's actually happening. So the do notation that we learned when Irfan taught us about IO is syntactic sugar for bind. So it allows you to express the same thing that you can do using the bind operator, but in a much more imperative style. So more like the type of sequential programming that we're used to in non-functional languages like JavaScript or Python, for example. So that makes it a lot easier to construct functions like this. But if I have a sequence like this, right? And each of these things has the return type of IO unit. And the next action that is happening here doesn't depend on the value that the previous one is returning, because I don't need this unit value to print another string. I already have my string here, right? So this is an instance of where you'd use the sequence value whenever you don't need a return value from the function that comes on the left side in order to execute the one on the right. And basically all you want to do is make these things actually happen, right? So you want the string to actually print. And then after that, you want the next one to print. And then after that, you want to get some input from the user, right? That's when you use this one here. It's used less commonly than bind, because typically we're composing functions together and those functions have some kind of meaningful result that we want to then use as an input to the next step in our program, right? But in cases when you're doing things in IO where you're just kind of executing side effects and not really passing values down through a pipeline, then you can use this one instead. But don't worry about this one as much as understanding what's going on in here. This is more important, right? Cool. I'll share this code and I'll share the link to this as well too. But definitely, if you have access to the Get Programming with Haskell book, I definitely recommend reading it and doing the different exercises and stuff. It'll be helpful. And if you really want to go deep in it, then you can use the First Principles book as well too. Good. I'm glad. Thanks for joining us. And yeah, what do you guys think? Did this format make things a bit more clear than just the live coding, seeing the diagrams and then actually defining the instances like this?
Yeah, that diagram was definitely helpful.
Definitely.
Cool. Because this is like my dry run or test run for when I teach this in my batch. So I just kind of improvised this on the fly today, but I'm probably going to reuse this and teach it in my lesson when I get to this stage with them, because it seems like the feedback was positive from you guys. So it's good to know.
Cool. Thanks a lot, Ian. I have to go. Take care and we'll see you soon.
Okay.
Bye, guys.
Great. Take care.
Thanks.
Thanks, Ian. Have a good day.
Thanks.
Yeah, you too.
Bye-bye.
Bye.